This video is for the Edexcel GCSE in Astronomy, Topic 10, Solar Astronomy. In this video, we're going to look at how to observe the sun safely. We're going to look at the different parts of the sun. We're going to look at sunspots and how they relate to the solar cycle. And finally, we're going to look at the effect of solar wind. So the most important thing here is that you must never look at the sun directly, and you must never look at the sun through a telescope. Doing so could be very damaging to your eyes. So there are two methods for looking at the sun that you can do safely. The first is to use a telescope pointed at a screen like this, and the second is to use a special kind of filter. Now, when you use a telescope pointing at the screen, you're just going to get a white screen unless you put something here to shield the screen, to produce a shadow on this screen. So just a piece of cardboard box will do. Cut a circle in it that's the same size as the telescope diameter. Cut a slice through it so that you can fit it over the telescope. Fit it over the telescope, and then put a piece of paper to act as a screen. And you can move the position of that paper until you see a nice image of the sun. Now, with this method, you can see things like partial or total solar eclipses. Here's a picture of a partial solar eclipse. But you can also see sunspots when the sun is particularly active. And we'll talk about sunspots towards the end of this video. The second method is to use a special kind of filter. And some telescopes which are designed for solar astronomy have these filters built into them, such as this one here. But otherwise, you can buy these filters and you fit them over the aperture of your telescope. They're not cheap, they are a pretty sophisticated piece of kit. Filters absorb all wavelengths of radiation, of electromagnetic radiation, except for those that the filter is designed to allow to be transmitted. The H-alpha color is 656 nanometers. And it refers to this particular line on the emission spectrum of hydrogen. So if you take hydrogen gas and you get it hot enough, you get it excited enough, it will glow and emit certain colours. It emits colours corresponding to these coloured lines on this emission spectrum. Now, the sun contains a lot of hydrogen, so there's a lot of very excited hydrogen there, which means these colours are emitted by the sun. But also the sun emits ultraviolet. It emits huge amounts of visible light which can cause blindness and other things. So these very special filters can be purchased, which you fit over the end of your telescope, which absorb all of the wavelengths of electromagnetic radiation except for 656 nanometers. That's the H-alpha line. H is for hydrogen, alpha because it's this dominant line here. It's a very deep red line. Now, with an H-alpha filter, the sun will appear red. You'll be filtering out all of the other colours except red. And so you'll be filtering out ultraviolet, which is particularly damaging to the eye. And I must stress here, you can't just use any old red filter to look at the sun. It has to be one that's designed for solar observation, because that will absorb enough of the dangerous radiation and allow enough of the red light to get through for us to be able to see the features of the solar surface that we're interested in. Don't try to use cheaper alternatives. Don't try any fancy tricks like using welder's goggles or anything like that. If you're going to observe the sun, do it safely. It's not worth the risk to try to cut corners. So now let's delve into the sun. And starting from the very middle, we're going to work our way out, all the way out to the atmosphere around the sun. So the core of the sun is about 150 times more dense than water is under normal conditions. Water density is about 1 gram per cubic centimeters. So the core in the very center of the sun is 150 times more dense than this. The temperature is huge. 15.7 million degrees Celsius, that sort of region. And you should know these numbers. That is a huge temperature. The diameter of the core is between 20 and 25% of the full diameter of the sun. Now, you'll find things online saying that it is the hottest place in the solar system. In fact, we have managed to generate temperatures hotter than this in the lab, but on a very small scale. Temperature is related to the average kinetic energy of the particles in a system. And so if we don't have very many particles, for example, we're colliding beams of protons at CERN, then you're able to get temperatures in excess of 15.7 million degrees Celsius, but on a very, very small scale. Now, at these sorts of temperatures, nuclear fusion can take place. And I'll talk about nuclear fusion in a bit. Nuclear fusion is where protons join together and form new elements. For example, they can form isotopes of hydrogen, or they could form helium, or even larger than that. But fusion can't usually take place at lower temperatures. The high temperature means that the protons are moving so fast that they're able to get close enough together for fusion to happen. There are lots of protons in the sun's core because protons are the nuclei of hydrogen atoms. Well, normal hydrogen atoms, the most abundant isotope of hydrogen. And where are the electrons? Well, they're in there as well, but because of the high temperature, the electrons aren't bound to those nuclei anymore. So we have a very hot plasma in that center, a very dense hot plasma. And almost all of the heat generated in the sun is generated in this 20 to 25% volume of the sun in the core. Moving outwards from the core, we have the radiative zone. That's this region around here. It extends to about 70% of the diameter of the sun. Now, the density in this radiative zone drops. It drops to about 0.2 grams per cubic centimeter right at the outer edge of the radiative zone. Now, that is lower than the density of water. The temperature in the radiative zone is as high as 7 million degrees Celsius, but it gets cooler the further away from the core you go, to about 2 million degrees Celsius right at the edge of the radiative zone. Now, there are different heat transfer mechanisms. There's conduction, where molecules collide with each other and transfer energy. And there's convection, where less dense, warmer molecules will rise above the more dense, cool molecules, which sink below when there is a gravitational field. That can't actually happen in the radiative zone because the difference in temperature isn't enough. The temperature gradient is too low for there to be convection. So instead, the main way that heat is transferred from the core through this region of the sun, which is where nuclear fusion is not taking place. It's not dense enough for nuclear fusion to take place. It's not hot enough for nuclear fusion to take place. But in this radiative zone, heat will transfer through radiation outwards from the core through this region. The imaginary line that separates the radiative zone from the convective zone is called the tachocline. Now, I don't think tachocline appears in your GCSE, but I'm including it here for completeness. There's some important and interesting physics that happens between the radiative zone and the convective zone. For example, in the radiative zone, the entire body of the sun rotates uniformly. That means that near the poles of the sun, so this part of the radiative zone up here perhaps, if we think that this is the axis of rotation through here, then this top part here will rotate once every, I don't know, whatever the period of rotation is in the center of the sun. And it will also rotate once in the same period of time near the equator for this radiative zone. But in the convective zone, that isn't the case. In the convective zone, along different lines of latitude, you'll have different rotational periods. And it rotates faster near the equator of the convective zone than it does near the poles of the convective zone. So this line that separates those two is the tachocline. Now, because of the interesting physics that happens, you're going to get shear around this region, this imaginary line, because part of the sun is going to be rotating faster than another part of the sun. Some people, some scientists have proposed that that's the origin of the sun's magnetic field, the prevailing magnetic field of the sun. There are a few different models that are proposed, and we don't yet know which model is the most accurate. So this is ongoing science research right now. A lot of scientists think that it's along the tachocline that the sun's prevailing magnetic field originates. And then we enter the convective zone. Now, the convective zone, I think, is absolutely fascinating because the density drops to about 1/6000th of the density of the air at sea level. So we're not talking about the density of water anymore. We're talking about the density of air, which isn't very dense at all. We can move through the air without any real fuss. And 1/6000th of the density of air is the density of the convective zone right near the outer edge. The temperature drops from about 2 million degrees Celsius right the way down to about 5,400 degrees Celsius. And because there's such a big difference in temperature over this space here, we can have convection. So within this region here, the plasma cycles around. It drops down, it gets hotter because it's closer to the radiative zone, and that warmer plasma rises up towards the edge of the convective zone where it cools and then falls back down again to the radiative zone. And all that is happening in the convective zone. When you think about the size of the sun, that's about the full extent of that convective zone. There's a little bit on the outside, but that's pretty much it. Now, from the core right the way out to the convective zone, the very outside of the convective zone, we have heat transfer by conduction and by radiation. But in the convective zone, we also have heat transfer by convection. It's too cool for nuclear fusion to take place in stars the size of our sun, but it's still hot enough that we have a plasma. The gas, the hydrogen mostly, is still ionized. The diameter of the sun is about 1.4 million kilometers across, and just 400 kilometers is the depth of this photosphere. Photosphere, the very edge of the convective zone, so it's got the same sort of density as the convective zone. Temperature's about the same as the edge of the convective zone, dropping right the way down to 3,700 degrees Celsius. And because it's so thin, it's not very opaque. It's very transparent. Because of the plasma in the convective zone, you can't see through it. It's completely opaque. So the photosphere is the deepest part of the sun. We can actually see, when you see photographs of the sun, that's as far as you can see in, the very edge of the convective zone. And so you're looking into the photosphere to see that. But just above that photosphere is something called the chromosphere. So photosphere, photo is light, sphere is a sphere, you know what that is. Chromosphere, chromo is colour. So called because it's got this deep red colour. And what's really interesting about the chromosphere is it's a region where the sun starts to get a higher temperature as you continue to move out from the middle. The density is dropping. I mean, I was a little bit tongue-in-cheek when I wrote this. Rather than putting it in standard form, I thought I'd write it out in full, which I know is a bit ridiculous. But that's a tiny density, very, very low density. It's about 10 to the negative 8 times atmospheric pressure of the air at sea level. So very, very low pressure. And the chromosphere extends out for another, well, between 3,000, 5,000, maybe a bit further than that, kilometers. It's not even. There's bits where it's a bit thicker, bits where it's a bit thinner, and it changes. It's dynamic as well. Now, you can't usually see the chromosphere because of how sparse it is and because of how bright the photosphere is. The light from the photosphere just passes straight through the chromosphere, and any light generated by the chromosphere is not bright enough for us to be able to see. But you can see it sometimes when, for example, there's an eclipse blocking out the light from the photosphere. Then we can see the chromosphere, and it's got a deep red colour to it. So one of the mysteries that we're trying to investigate and figure out is why it is the temperature is increasing as you move up. We have a lowest temperature at the very edge of the photosphere of about 3,700 degrees Celsius. But if we carry on going further out from the sun, the temperature goes up. Part of the reason for that is that the density goes down so much. Remember, temperature is related to the average kinetic energy per molecule. And the molecules are sparser. They can move further between collisions with each other. So they can be moving faster, which means that you can have higher temperatures. That's not the full story, though, and there's a lot of research still going on into this area. Beyond the chromosphere, you've got the corona. Unfortunately, the word corona now generates shudders from people who have lived through 2019, 2020, 2021, and I don't know when you're watching this, but it's probably still going on, the coronavirus pandemic, but this is unrelated to that. Okay, so the corona. This is the atmosphere of the sun which extends outwards, and it extends a long way outwards, about 20 times the radius of the sun. It just carries right out into space, and about 10% of the way, it is written here, about 10% of the way to the Earth. Huge region. Density varies a lot in this region, but you can see it's not a high density. The density isn't the same everywhere in the corona, but it does drop lower than it is in the chromosphere. And the temperature can go as high as 1,000,000 degrees Celsius, or even higher in certain regions. And again, it's partly because of how sparse that atmosphere is. Now, why does it get so hot? There are other explanations, and there are quite a few of them. Some of them talk about magnetic induction, like if you have a magnetic induction cooker, then you might understand a little bit about how induction works. Varying magnetic fields can induce currents, and that can accelerate positive charges. So it's possible that something to do with the sun's magnetism causes an acceleration of the plasma within the corona. But we're not really sure, not at this stage. Now, this plasma that flows away from the sun is the solar wind. And we'll talk about solar wind a little bit later on. Now, I want to talk about nuclear fusion, the processes that are happening within the sun's core. And there are a few different types of nuclear fusion that go on, a few different proton-proton chains, fusion chains, and there are other fusion reactions as well. For example, something called the CNO cycle of fusion. But in your GCSE, we're only concerned with one type of proton-proton interaction, one type of proton-proton fusion chain. And that's what we're going to look at here. About 3/4 of the mass of the sun is hydrogen, and about 1/4 of it is helium. Well, not quite, because there's some other stuff thrown in there as well, but that's the majority of what makes up the sun. In fact, astronomers often say there are 3 elements that make up the universe: hydrogen, helium, and metal. And everything else down here is just referred to as metal. The periodic table of the astronomers. They've got a sense of humour. But this is our sun, a 3rd-generation star. This is what our sun looks like. As a physicist, I get a bit grumpy when people that use the joke don't trust atoms, they make up everything. Because, of course, atoms don't. What we're looking at here are ions, because in the sun this is a plasma, so they're not atoms for a start. And the second thing is that the mass that you find, which is baryonic, which is what we refer to this sort of matter is about 4% of the mass of the energy mass that is in the universe. It really isn't very much. So I jokingly take the mick, have fun with chemists and say that they're interested in a tiny fraction of 4% of what's made up of the universe, and physicists are interested in the rest, but there we go. So let's look at this interaction. We start with 2 hydrogens which are travelling fast enough to overcome what's called the Coulomb barrier. The 2 protons, which are the nuclei of these hydrogen atoms, remember the electrons have been stripped off because of high temperature. So these 2 hydrogen nuclei, these 2 protons, repel each other because they have the same charge. So as they move towards each other, they slow down, slow down, slow down, stop, and then start to accelerate away from each other. Well, they're always accelerating away from each other. Let's get the physics correct. But they slow down, slow down, slow down, stop, and then move away from each other, getting faster and faster as they move away from each other. If you get those protons moving fast enough, then they can get close enough for another force to kick in. The strong nuclear force is stronger than the electrostatic repulsion and can stick these 2 hydrogens together, join them together into a single nucleus. That nucleus isn't stable, so the weak nuclear force causes one of those protons to decay into a neutron. That proton turning into a neutron emits a W+ boson, which will decay into a positron and an electron neutrino. Now, there's a lot going on there. There's some good particle physics in this interaction. And if you're interested in that, I have a series of 12 videos all about particle physics that you can look at. Have a look on my YouTube channel for details. It's particle physics series of videos. It's worth watching. It's about 2 hours long. So there's some interesting physics that's going on in here. And what we're left with is, well, it's still hydrogen because there's still one proton, but it's deuterium. It's a less abundant isotope of hydrogen. And this can fuse with other hydrogens to form helium. And then helium can form with helium to form helium. And some spare protons fly off. So when you look at the whole of this chain, we start by putting in 1, 2, 3, 4, 5, 6 hydrogen atoms. Actually, 6 hydrogen nuclei. That will then go through a series of processes, and what comes out is 1 helium nucleus, 2 hydrogen nuclei. We also have 2 positrons being emitted, which I've indicated here, and 2 electron neutrinos emitted, which I'll indicate here. And the other thing that comes out of this is tremendous amounts of energy. Now, the thing that students find really perplexing, and I find absolutely fascinating, is that if you add up the mass of these protons here, you add up the mass of all these 6 individual protons, it comes to less than the mass of these 2 protons plus the mass of this helium nucleus. Okay, that makes sense. E equals mc squared, and energy's been released, so mass should be reduced, and that's fine. Except the mass of a neutron is higher than the mass of a proton by a tiny amount. So the mass of a neutron is higher than the mass of a proton by a tiny amount, but overall there's less mass afterwards than there was before. You can see that that becomes difficult to reconcile, and your understanding of what makes mass, what is mass, is fundamentally flawed. I did something recently on a tutorial about nuclear physics and nuclear energy and binding energy where I go into this in a bit more detail. One of the last episodes in Series 3 of my weekly tuition sessions, which if you want to watch, you can subscribe to my YouTube channel and you get notified when I go live. It's going to be every Tuesday at 6 o'clock in the evening UK time. Well, for Series 4, we'll see how it goes. So this is what's happening within the core of the Sun. And this and a few other proton-proton interactions as well, and some other nuclear fusion, which is going to form some of these heavier elements. But this is what's happening. I'm very grateful, actually, to all these websites that make various astronomy pictures publicly available for free. It really is helpful. For example, anything that NASA has produced is in the public domain. Wonderful. That means that I can use it. So let's dig into sunspots. You'll see photographs of sunspots like this, really magnified, or videos of sunspots moving across the surface of the sun like this, and you can see how they evolve and change. And they look like black spots, very dark spots. In fact, there's still an awful lot of light being emitted by those spots, but it's just less than the region around them. So when you adjust the contrast of your picture to be able to see the sunspots, they end up looking black. The reason why they emit less light is because these are regions where the temperature is lower. Now remember that convection is this flow of charged matter, this charged plasma inside that convective zone of the sun. What these sunspots are where the magnetic field lines coming out of the sun's surface at those points is a little bit stronger. There's a bit higher concentration of magnetic field lines, what we call magnetic flux. And that actually inhibits that convection in that region, which inhibits putting fresh, hot solar material near the surface. So the surface cools down a bit more. So you usually find these sunspots where the field lines emerge from the surface of the sun. So that's what a magnetic pole is, where field lines emerge from something or go into something. That's called a magnetic pole. The sunspots themselves, they start small, they grow, and then they shrink. And you can see that happening. They expand and contract. And they don't drift north or south. They stay going around these lines of latitude around the sun. Now, the sun has an 11-year cycle that we're going to go into in a bit later in this video. You get more sunspots when the sun is more active, and fewer sunspots when the sun is less active. Sunspots are linked to solar flares and things like that, to what we call coronal mass ejections. That's solar flares that spit out loads of solar mass into space that flows through space and eventually it could reach Earth. So here's a little video which is in the public domain. Thank you very much to Wikipedia and to NASA for this. And we're going to look at the very middle here, and you'll start seeing some sunspots appearing. They'll appear in a moment. Now, a reason why I've mentioned about this being in the public domain is because I don't want people complaining and saying that I'm breaking copyright. I'm really not. So you can see the sunspots have appeared here, and they move around a little bit. And we're moving the camera, if you like, whilst these sunspots are moving. So we're keeping these near the middle and watching how they evolve. You'll see they've got larger, and some of them stick together. And as we get towards the edge of the sun, they start to shrink and contract again. And that's the general way that they evolve, although they're starting to contract now, not as much as they grew, so they'll contract when they're a bit further around the edge of the sun, perhaps. And that's how sunspots appear to change as they go around the sun, along those lines of latitude. It's quite handy because you can use sunspots to work out the rotational period of the sun. What you can do is you can time how long it takes for a sunspot to move from one edge of the solar disk to the other edge of the solar disk, and then double it. And that should be how long it takes for the sun to rotate. It's a very simple calculation, but it can take a long time, many, 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 many days, and you don't want to be trying to observe the sun for that long. One reason for that is that there could be cloud cover at some point in that month that you're watching the sun. So instead, you can do shorter measurements, shorter periods of time, observing sunspots, maybe a few days apart, and then extrapolating that. The thing you have to be careful of is that because the sun is a sphere, or close to a sphere, no Blake spheroid, because the sun is spherical, the spots will appear to move faster across the middle of the solar disk than they do the edges. They'll appear to look slower near the edge of the disk, even though the sunspots are moving at a constant speed, just because of perspective. So we can do some clever maths here, which I'm going to walk you through. First of all, let's assume the sun is spherical, and the radius of the sun is half the diameter, which I've labelled here. There's the diameter of the sun I've labelled here. And imagine we're somewhere to the left over here, observing the sun. And we observe a sunspot appear at the very edge and move around to some point here, and the distance that we observe the sunspot move is x. So that has moved around what we call an angular displacement of theta. What you can see here is I've drawn another line here which I've labelled L, some length L, which forms a right-angled triangle. Because it's a right-angled triangle, I can do Pythagoras. I can say that this length here, which I'm highlighting with my cursor at the moment, that length there, is going to be equal to d, the full length, well, half of d, which is the length from the middle of the sun to the edge, minus x. So half of d minus x is this length here. That length there is just half d minus x. And so half d minus x squared plus L squared should be equal to half d all squared. That's Pythagoras. It's a right-angled triangle, and that's what I've written at the top here. Now you can do some maths. You can rearrange this to get L squared as a subject and multiply out the brackets, and you end up with this expression here. That L squared is equal to xd minus x squared. And if you don't believe me, please go ahead and work through that algebra yourself. You should be able to do that yourself. Now we're going to use trigonometry here. The sine of this angle here is equal to the opposite divided by the hypotenuse. So L divided by D divided by 2 is the same as 2L divided by D, which I've written here, and sine of theta equals 2L divided by D. Why am I doing that? Because I need to know what theta is. Because the sunspots would move 360 degrees if they move in one full rotation. So if I do 360 degrees divided by the angular displacement of the sunspots, and then multiply it by the amount of time it took to do that angular displacement of the sunspots, that tells us the total time it would take for the sunspots to move all the way around. That's the rotational period of the sun. So we have an expression for theta here, Theta is just the arc sine, or sine to the -1 of this mess here, which I can substitute in for theta there to get this expression here. And finally, we know what L is. L is the square root of xd minus x squared, which we can plug in here. So this complicated looking equation at the bottom just comes out of what we call trigonometry, Pythagoras, some geometry. It comes out of geometry. And what if you don't start by observing the sunspot right at the edge? It's somewhere else. Well, we can do the similar thing. We can measure the time it takes for the sunspot to move from here to here, and then we can draw our diagram and use trigonometry to determine what the time period is. But I'll leave this expression here. This is some good problem solving for you. I doubt you would get anything quite as sophisticated as this in your GCSE in astronomy, but I've included it here for completeness and because it's some good science. So that's the solar rotation period. Now, if you do those observations of features on the solar disk as they move along those lines of latitude, what you find is that it takes about 35 days near the poles for the sun to rotate and about 25 days near the equator. Well, 24.5 days on the equator and 38 days right at the poles. Remember that that is not the case in the radiative zone within the just outside the core of the sun. The rotational period there is the same no matter what line of latitude you look along. Whatever your longitude is, it doesn't matter. But here you can see that it does matter for everything outside that, beyond the tachocline. And I've already mentioned my gratitude to NASA for making everything public domain. Here's a beautiful mosaic which shows the sun, photographs taken with different filters and different sensors to detect different parts of the electromagnetic spectrum, or even other effects. For example, there's a very clever Doppler effect that they can use to visualize where matter from the sun is moving away or towards us. We can use that to look at vibrations on the solar disk, that sort of thing. But I can't make head nor tail of this picture, so this picture I think is a bit better. Again, thank you very much, NASA. Now, I'm not going to go into a lot of detail about this. You can pause the video if you're interested and have a read of some of the things that are here. It tells you what each of these different types of images, what each of these different images shows you underneath there. But as a basic rule of thumb, the smaller the wavelength, the more energetic the electromagnetic radiation that we are visualizing. This unit, A, with a circle over the top, is the angstrom. It's equal to 10 to the negative 10 meters. So the more energetic, the hotter features in the sun can be visualized if you look towards the lower end of this list, although I've just noticed it isn't quite in reverse numerical order. But there we go. You can see that this is pretty much what we see with visible light. This is what we see, just a disk with some sunspots on it. But where those sunspots are, you can see very active solar flares being spat out in these sorts of regions. You can see the corona in this sort of region. So there's electromagnetic radiation being emitted of about 193 angstrom wavelength, which you can't see when you just look at visible light because of how bright the visible light is. You can't get the contrast to view that corona, unless, of course, it's an eclipse. So we've looked at sunspots a little bit, and we've looked at how we can use those to measure the rotational period of the sun. Now we're going to look at another cycle that the sun undergoes, and it's nothing to do with the rotational period. This cycle is 11 years. Start this little video there. What you're looking at here is a picture of the sun with those sunspots on it, and we're stretching it out so that we can see a map of the whole surface of the sun. And over a period of 11 years, let's see what happens. You can see that right now there's not very many sunspots. There's not a lot of activity. But then it starts to pick up. There's more and more of these sunspots. They move closer and closer towards the equator, and then it calms down again. And then it starts getting a bit more active, and it gets very, very active again, and then it calms down again. And that cycle is 11 years. If we were to look at a picture, so we can see it all as one picture rather than a video, we get something that's often called the butterfly diagram. Let's look at the picture on the top. On the y-axis, you can see the different latitudes of the sun. So the further north, this is the north pole of the sun, this is the south pole of the sun down there. And what we're looking at is a certain area. We're getting the same area strip on that particular latitude. And the colour indicates how much of that strip is covered in sunspots. The percentage of the area. So it's the same area for each, equal areas. So it is the percentage of that area which is covered in sunspots. And the yellower the picture, the more of that area is covered in sunspots. Red is a little bit of sunspots, black is very little, white is just none. And the x-axis is time. So you can see that sunspots start appearing nearer the poles. I say nearer the poles, it's just larger latitudes. And then over time, those sunspots drift towards the middle, towards the equator. And then there's a period where there's very little sunspot activity. And then the sunspots get more active again, starting at higher latitudes and getting closer and closer and closer to the equator. And then a period of dormancy again, and so on. You possibly also see that there appears to be fewer sunspots here than there is here. That hints that there are other cycles within the sun, but I'm not going to go into those. So you can see the movement of the sunspots over time, but you can also see when things are more active, when there's a lot of sunspots. For example, the early 1960s or even late 1950s, loads of sunspots. But then if we go forward to about 1965, very, very few sunspots. So there are regions where there are times when it is more active and times when the sun is less active. And that coincides with an 11-year cycle for how bright the sun is. So if you look here, we've got sunspot observations in blue, this blue line that's going up and down, and the year is on the x-axis. And then we've also got what's called irradiance in black. That is how bright the sun is. The yellow, these lines that go up and down, are the daily irradiance. There's obviously a lot of variation there. But over the year, that's what's on red here. It also corresponds to solar flares. There's more solar flares when the sun is brighter, when there's more sunspots. And this 10.7 radio flux, as radio wave emission as well, seems to coincide. Now, you're probably thinking you don't see the sun get much brighter or dimmer. Well, no, it doesn't change a lot. If you look at the numbers on this y-axis, they're very, very similar numbers from down here. Gets down to about 1,365.5 all the way up to about 1,366.5, roughly. So there's not a huge variation in solar irradiance in watts per square meter. Not a huge amount of variance, but it does vary. So 1980s, early 1980s, the sun was actually emitting more heat than in the mid-1980s. And the 1990s emitting more heat than in the mid-1990s. This is completely unrelated to global warming and climate change, where this sort of trend is still going on. The sun's still doing what it does, but the global temperature has been increasing in a way that doesn't match this at all. So let's talk about solar wind then. There's these charged particles, this plasma, that is emitted from the sun, streaming outwards from the corona, and it continues beyond the corona, right out into space. The solar wind extends right the way out to the very edge of our solar system, where gravity is constantly pulling on it backwards, so eventually the solar wind stops, and we have a region at the edge of our solar system where the solar wind has stopped and starts to fall back in. The majority of the solar wind is made up of electrons and protons, with a few alpha particles and maybe some other trace elements in there as well, but it's mostly just electrons and protons. The reason why they're able to get away from the sun is because of those high temperatures, that high average kinetic energy per molecule, per particle. Now there's a small list of phenomena that are caused by the solar wind that we're going to go into now. So the first one I wanted to talk about is the tails of comets. Often comets are drawn incorrectly with a tail going in the opposite direction to where the comet is moving, like the comet's somehow a fireball moving through space with a tail of debris left behind it. But that's not quite the way it is. So if you look at the comet moving around the sun here, When the comet is over here, the tail's actually pointing in the same, roughly the same direction. The comet's moving. It's moving in this direction, and the tail's pointing in this direction. So what's actually happening here is we have two tails, and we'll go into comets a little bit more detail in a later video. One of those tails has more mass because it's made of the dust that's emitted from the comet as it approaches the sun. And so because of that and the momentum of the dust, it leaves the comet trail in a slightly different direction to this gas tail. It's a much lower density tail. And the heat from the sun ionizes that gas, which is emitted due to the heating of the material of the comet, those volatiles inside the comet. And it causes the tail to glow. And that glowing tail always points away from the sun because the solar wind pushes those gases in that direction. Another thing that's caused by the solar wind are the aurorae. So the aurora borealis on the northern hemisphere and the aurora australis in the southern hemisphere. The solar wind here is deflected by the Earth's magnetic field, the Earth's magnetosphere. Looks like the usual bar magnetic field shape, but stretched out in a direction away from the sun. There's a lot going on this diagram that we don't really need to worry about too much. But as the solar wind comes in, it gets deflected by the Earth's magnetic field, spirals inwards into the north and south hemisphere, towards the north and south pole. And it produces these beautiful shimmering patterns in the atmosphere. As those charged particles enter the atmosphere, they collide with the molecules in the atmosphere, particularly the nitrogen and the oxygen molecules, and excite them and produce these different coloured images. Now, at the upper atmosphere, there's more of what we call atomic oxygen. That's oxygen that's no longer bound to other oxygen. Because of the radiation from the sun and from elsewhere, the O2 molecules get split into atomic oxygen. And it's easier to ionize atomic oxygen. So you tend to get these different colors corresponding to different excitation states of oxygen and nitrogen as well, but mostly oxygen in the upper atmosphere. And so you can see here's a video from the International Space Station as it flies over the southern hemisphere. And this is looking at the aurora australis. And you'll see that there is a red glow and beneath that a green glow with these beautiful ribbons. I mean, this is a series of still images, so it wouldn't quite look like it shimmers as fast as this video would imply. But it's still, you can see some movement of the aurora as those ribbons of green light move around. And the red is happening at the very highest altitudes where there's the most energetic oxygen because there's less air around, it's lower density. As you move deeper into the atmosphere at those lower altitudes, you get those beautiful green ribbons in the aurora, and even lower still, apparently you can see blue, although I can't recall ever seeing it. You can also sometimes see yellows and things like that, but they're often just a combination of these other colours. Red and green combined make yellow, for example. So you'll tend to get more aurorae when the sun is more active every 11 years. And sometimes the sun can be so active that those aurorae can be seen as far south as maybe even the tropics, I think, in the past, when the sun's been particularly active. But usually you're only going to see these up near the Arctic and Antarctic circles. Another effect that will happen with solar wind are geomagnetic storms. So geomagnetic storms are where the solar wind interacting with the Earth's magnetic field gets deflected so that it can enter the Earth's atmosphere. But sometimes there's a lot more mass in that wind, what we call a coronal mass ejection. More of those protons and electrons in that solar wind. It's more dense. Now, when that happens, it can do interesting things to the Earth's magnetic field. Charged particles moving have their own magnetic field. So as this stream of charged particles from the coronal mass ejection enters the Earth's atmosphere, it changes the Earth's magnetic field. And that can do things like inducing currents. In the old, there's a famous story from the late 1800s where telegraphers got electric shocks from their Morse code telegraphy machines. You know, they're pressing a button and then sending dots and dashes through the telegraph cables, but the telegraph cables don't usually carry very much current. The changing magnetic fields caused by these geomagnetic storms induced currents in those cables, which gave the operators electric shocks. So geomagnetic storms comes under the general category of space weather. It can affect communication satellites. It can cause satellites to their electronics to get damaged because of inducing currents by those changing magnetic fields caused by the interaction of the solar wind with the Earth's magnetic field, which can cause disruption to GPS. It also increases radiation exposure. This solar radiation increases radiation exposure for anyone that goes on planes, pilots, passengers, or anyone that's up in space, any astronauts. And there's other things, for example, cables. Big cables that are laid out, usually for communication and carry very small currents, can have much higher currents induced in them, which can damage other electronic systems. The last thing I want to look at are the Van Allen belts. Famous from conspiracy theorists who say it's a reason why we can't possibly have gone to the moon and things like this, which is of course nonsense. Because we did go to the moon. No great controversy there. Feel free to type in the comments if you think somehow I'm being untruthful. Maybe I'm part of the conspiracy. No, I'm not. So, Van Allen belts. The Van Allen belts are regions of charged particles that are captured around the Earth. And there's two different Van Allen belts. The inner Van Allen belt, which you can see here in brown, and the outer Van Allen belt, which is this blue hazy region that extends much further outwards. Now, the inner Van Allen belt is caused by solar radiation and cosmic radiation, causing there to be charged particles from the upper atmosphere, which leaks out a little bit into space. And so that's why you get this region here. That's more caused by the Earth's atmosphere becoming excited and ionized and leaking out. The outer Van Allen belt is caused by capturing that solar wind that enters the Earth's magnetic field and gets trapped in that sort of region. Now, when you pass through these Van Allen belts, you are exposed to higher doses of radiation. But you're not in it for that long. They're also not evenly distributed. So you can see here it's thinner near the tops. So near the bottom, near the poles. So when our astronauts went to the moon, they didn't actually pass through the inner Van Allen belt. As far as I remember reading, they passed nearer the poles so that they weren't exposed to that radiation. And they didn't spend very long in the outer Van Allen belt either, so they weren't exposed to radiation for very long. You can see that we've got certain things like our satellites, the ISS, for example, which is quite close to the Earth down here and stays within the inner Van Allen belt. There's a safe region between the two Van Allen belts where you can put satellites. But you can see GPS sits within the outer Van Allen belt, and we've got some telescopes and other things that sit within the outer Van Allen belt. And then beyond that, geostationary orbits, they're inside the Van Allen belt, the outer Van Allen belt as well. And they operate perfectly well. But the Van Allen belts could become more dangerous when there's a solar mass ejection, when there's a coronal mass ejection, because there's more charged particles entering it. So that can cause damage to satellites. And that's it. So we've talked about all those key points from the specification. And if you want to find out when the next video, topic 11's video, is produced, then please do click like. That means you get more of my videos suggested to you. And subscribe to my YouTube channel and you'll get those notifications. Thank you very much.